of the way because it's kind of definitional and notational, and then the other topics are more process. So this is a picture from earlier in the book in Calculus 1 section of the book. And it's showing a function. This is the function. It's showing a tangent line to that function at this specific value. I think I'll recall it A so it kind of stands out as like the point on the curve that you're specifically interested in. If I change this value by a little bit, I could evaluate the function at this new point. I could also evaluate the tangent line at the new point. The tangent line near my special value should be approximating the curve. And you can see right around this x value, the tangent line is doing a pretty good job of approximating the curve. But the farther I get away from that point, the less the tangent line approximates the curve. So one key idea is that the tangent line near x equals a approximates the function. We'll just say the function. Okay, that's one key point. In terms of some definitions, if I change my x value a little bit, the amount that I change it, we could denote by delta x. And in terms of our derivative notation, dx is equivalent to delta x. So what do we mean by that? Well, if I move over here, whether I'm evaluating the function or whether I'm evaluating the tangent line, the amount that I changed x is the same whether I'm focusing on the function or whether I'm focusing on the tangent line. If I move over by 0.01, I move over by 0.01. So that's what we mean by dx is equal to delta x. They're interchangeable. But delta y is not the same as dy. Delta y refers to the actual change in the function value from x equals this point to x equals this point. Whereas dy refers to the difference in the y-coordinates on the tangent line. So dx will equal delta x, whether on tangent line or on function. Dy does not equal delta y. Instead, dy is difference in y's on the tangent line, and delta y is the difference in y's on the function. And if you take the idea that this is denoting, the derivative of the function at x, you can approximate, well actually this is true, but you can approximate delta y by finding the derivative of your function, evaluating it at the point that you're interested in, and then multiplying that by what you changed x. So whether I write dx or delta x here doesn't matter, but again, dy is definitionally equal to what I wrote here. If you were trying to approximate
how much does my function change, you could approximate that by finding the derivative of the function, evaluating it at the point you're interested in, and then multiplying it by how much you plan to change x. So let's suppose your function was a profit function, and you were interested in how much will my profit change if I increase my production from 5,000 to 5,100. Okay, changing from 5,000 to 5,100 is changing by a little bit relative to 5,000. Okay, so you could approximate the change in your profit by taking the derivative of your profit function, plugging in the 5,000, and then multiplying by what? What is my delta x in this case?
0.1.
100?
It's 100, right. I changed x by 100. So my example, I would have my profit function derivative evaluated at 5,000 times 100, and that would be approximating the change in the profit. The tangent line is called the linearization of your function, and it makes sense. You're taking your curved function, you're approximating it with a line. The closer you are to the point at which you found the line, the better the linearization is going to approximate your function. I'm reviewing all of this because all of these concepts can also be applied to multivariable functions. We just increase the number of variables that we have. And so the next picture, I'm going to flip now my book to chapter 14, and there's a similar picture, but instead of just a two-dimensional function, we have a three-dimensional, it's going to be a picture of a three-dimensional function. But the idea applies even if you have higher than 3 dimensions, you just can't draw a picture of it.
That's like 8 cups of coffee. Even the great Cordero.